Hello, this is WE391 Power Electronics. Today we will have a lecture on boost converter. And the textbook that we are going to use is written by Daniel Hart. This is a textbook that is widely used in many universities in the United States. I will cover Chapter 6.5 in today's lecture. Before starting the lecture, let's take a look at the learning objective. After today's lecture, students would be able to comprehend the working principle of boost converter. And also, they will learn the technique to analyze DC-DC converter, and they can apply the techniques they learned to analyze other types of DC-DC converters, for example, buck converter or buck boost converter. And also after today's lecture, students should be able to answer all the questions on my lecture note. The lecture note will be handed out to students at the beginning of class, and it has 14 questions. And also I will upload the electronic version on the learning management system on Canvas. And I would use think, pair, and share strategy during my teaching. So students will be asked to think individually and also work in pairs for the discussion. And they are also encouraged to share their ideas with other students. In order to ensure student engagement, I will use student response systems such as iClicker to take polls during my lecture. Before introducing the boost converter, I would like to introduce the basic principle of DC-DC converter first. So the first question is, what is DC-DC converter? This is the question for some students that without the power electronics background. So the DC-DC converter is a circuit that converts a DC voltage to a different DC voltage level, providing regulated output. An example is the solar panel. So thus for the solar panel, the output voltage is 18 volts. That's the input to the DC-DC converter. And the output of the DC-DC converter is 380 volts. So it converts the low voltage to high voltage. So this is called boost converter. But we can also convert the high voltage to low voltage. But today we will discuss boost converter, whose output voltage is greater than its input voltage. First, let's take a look at a very basic DC-DC converter as shown in Figure A. So it consists of a voltage source, and the voltage is represented by Vs. The subscript S stands for source, and the load is a resistor RL, and the output voltage is represented by VO. And we also have a transistor here. The transistor works as an electronic switch in power electronic circuit. So we can use a switch to replace the transistor and obtain the equivalent circuit as shown in Figure B. So the electronic switch has two states, that is when the switch is closed and when the switch is open. So for the power electronic circuit analysis, we need to discuss two scenarios, that is when the switch is open and when the switch is closed. So first, let's take a look at the scenario when the switch is closed. When the switch is closed, the voltage Vs is in parallel with the load. So the output voltage VO equals Vs. So we can plot the waveform of the output voltage. When the switch is closed, we assume that the switch is closed when time is between 0 to dt. So during this time period, the output voltage VO equals Vs. Next, when time is between dt to t, we assume the switch is open. So when the switch is open, the load is not connected with the source. So the voltage, the output voltage VO equals 0 when the switch is open. So the switch is open for time 1 minus d times t. Here we have the definition of D. D is called duty ratio. It is T on over the capital letter T, the time of one period. It is a fraction of time when the switch is closed. So we obtain the waveform of the output voltage. It is a square wave. But what we care about is its average value, the average of the output voltage. So from the definition of average value, we can easily obtain the equation to calculate average value. That is by doing the integration in one period and take the average. After simplifying this integration, we obtain the relationship between output voltage and input voltage. VO is the output voltage, Vs is the input voltage, and D is the duty ratio, which is a value between 0 to 1. So from this equation, we know that the output voltage is smaller than the input voltage. And also in some applications, for example, the previous example, the solar panel example, the input voltage is not a constant because the voltage of the solar panel depends on many factors. For example, weather condition and also how strong the sunshine is. So the source voltage is not a constant. So in order to stabilize the output voltage VO, we can adjust the duty ratio D in order to stabilize the output voltage VO. So that's a brief introduction to the basic principle of a DC-DC converter. And also, I introduced the methods to analyze DC-DC converter. That is, discuss two scenarios, when the switch is open and when the switch is closed, and plot the equivalent circuit in these two scenarios, and plot the waveform. Let's take a look at the boost converter. Boost converter is also called step-up converter. So the output voltage is greater than the input voltage. And also the boost converter, its circuit is a little bit more complicated. And also the relationship between the input voltage and output voltages, we need to derive that. So figure A shows the circuit of boost converter. Before our discussion, we need to make some assumptions to simplify our discussion. Let's take a look at the first assumption, is that the circuit operates in steady state. We will use this assumption in question 12. The second assumption is that the inductor current is continuous. We call this continuous current mode. Obviously, we also have discontinuous current mode, but we will discuss discontinuous current mode in future lectures. We will discuss the requirement for the continuous current mode in question 13. The third assumption is that the capacitor is very large and the output voltage is held at a constant VO. We need to use this assumption in question 4 and question 9. But in reality, the capacitance cannot be infinitely large, so the voltage on the capacitor has some voltage ripple. We will discuss this in question 14. The fourth assumption is the switching period is capital letter T, and the switch is closed for time dt and open for time 1 minus d times t. This is the same with the previous example. Assumption 5 is that all the components are ideal. We do not consider losses. So after introducing these assumptions, let's start analyzing the circuit. So first, let's take a look the scenario when the switch is closed. So that is when time is between 0 to dt, the switch is closed. So we treat it as short circuit. And also in this scenario, there's a diode. The diode is reverse biased, so we treat the diode circuit as open circuit. So we can easily obtain the equivalent circuit. The equivalent circuit is very simple, and question 1 and question 5 are based on this equivalent circuit. Some questions are very easy, and some questions need a little bit thinking. So let's take a look at this question, and for each question, I will give you 20 or 30 seconds to write down your answer, and you can pause the video and check your answer with the solution. Let's take a look at the first one. What's the voltage on the inductor? Give you 20 seconds. So let's take a look at the circuit. So the voltage source Vs is in parallel with the inductor. So the inductor current VL equals Vs. So this is very straightforward. The second question needs more thinking, that it asks you to calculate the current change of the inductor when the switch is closed. So I give you some hint. In order to calculate the current change, we need to calculate the changing rate, and using the changing rate, multiply the time when the switch is closed. You can obtain the current change of the inductor. So for this question, I give you 30 seconds to write down your answer. Okay, let's take a look together. From the first question, we know that a positive voltage Vs is applied on the inductor, right? So the inductor current should increase because a positive voltage is applied on it, right? So we can calculate the increasing rate, which is Vs over L. It is increasing. And also we know that the switch is closed for time dt. So using the increasing rate multiply the time, we can obtain the current change. So Vs over L is the increasing rate, and dt is the time when the switch is closed. So we obtained the expression for delta IL closed. We will use this expression when we derive the relationship between the input and output voltage. Question, I think question 12, we will use this expression in question 12. And the third question is very easy, is straightforward, the diode current. So give you 5 seconds to write down the answer. Okay, so here the diode is reverse biased, so in the equivalent circuit it's open circuit, so obviously the ID equals 0. Question 4. What's the voltage on the capacitor? So this will use the previous assumption. We assume that the capacitance is infinite large, so the capacitor is in parallel with the load. So the voltage on the capacitor equals the load voltage VO. Question 5 is what's the current through the capacitor, and you can apply KCL on this node. So give you 5 seconds to write down the answer. So applying KCL on this node, because ID equals 0, so IC equals IO. But be careful that the reference direction is different, is opposite. So IC equals IO, but there's a negative sign here. IO equals VO over R. So we can obtain the expression for IC. So we finished analyzing the circuit when the switch is closed. When the switch is closed, the voltage source is charging the inductor, and also the capacitor is discharging, supplying power to the load when the switch is closed. That is when time is between 0 to dt. And question 11 asks you to plot the waveform. So now let's plot the waveform together. For the inductor voltage, we know that between 0 to dt the switch is closed and the inductor voltage VL equals Vs. So we can plot here. And also a positive voltage is applied on the inductor. So the inductor current should increase. And also we already obtained the change, the current change when the switch is closed. But what we do not know is the initial value. Here it is denoted as I minimum, and also the maximum value we do not know. We will introduce how to calculate these two values later. The third one is ID, that is when the diode current. so it's reverse bias, so the diode current is 0 during this time. And the capacitor current, the capacitor current equals VO over R, but be careful of the negative sign here. So that's the analysis of the circuit when the switch is closed. So next, let's analyze the scenario when the switch is open. That is when time is between dt to t. When the switch is open, the switch circuit we treat it as open circuit, and the diode is forward biased, so we treat the circuit as a short circuit, so we can obtain the equivalent circuit. And we need to answer question 6 to question 10 based on this equivalent circuit. Actually, question 1 to question 5 are the same as question 6 to question 10, but the equivalent circuit is different, so their answers are different. Let's take a look. So the first question is, question 6 is, what's the voltage on the inductor? Give you 5 seconds to write down your answer. So it's obvious that the voltage on the inductor equals Vs minus Vo. This is from KVL. From KVL, we can obtain this relationship. The question 7 is more difficult. What's the current change of inductor when the switch is open? Give you 30 seconds to calculate to obtain its expression. Okay, now let's take a look. First, let's take a look at the voltage applied on the inductor. We already obtained it on question 6. It equals Vs minus Vo. Here, there's another question. Is it a positive value or a negative value? Yes, it is a negative value, because for the boost converter, the output voltage is greater than the input voltage. So VL is a negative value. So let's think about it. A negative voltage is applied on the inductor, so the inductor current should increase or decrease. Yes, it should decrease. What is the decreasing rate? The decreasing rate is Vs minus Vo over L. And we know the switch is open for time 1 minus d times t. That this is a time. So using the decreasing rate multiply the time, we can obtain the current change when the switch is open. Question 8. How about the diode current? So now here the diode is forward biased, so it's in series with the inductor. So the diode current ID equals the inductor current IL. And question 9. What's the voltage on the capacitor? The same, we use our assumption. VO is constant, so VC equals VO. And also, if the VO is not a constant, the VC also equals VO because they are in parallel, right? Question 10. What's the current through the capacitor IC? Use KCL. So I give you 10 seconds to write down your answer. Okay, now let's take a look. So IC plus IO equals ID. So IC equals ID minus IO. So ID equals IL, as we discussed in the previous question. And IO equals VO over R. So we obtained the expression for IC. So we finished analyzing the circuit when the switch is open. When the switch is open, the voltage source is supplying power to charge the capacitor, and also it is supplying power to the load. So we can plot once we finish these calculations, we can plot the waveforms. So during time dt to t, a negative voltage Vs minus Vo is applied on the inductor. So the inductor current should decrease during this time. And also the ID equals IL, so we can obtain ID. And IC equals IL minus VO over R, we can obtain IC. Question 12 is the most important question for boost converter. We need to derive the relationship between the Vs and VO, that is the relationship between input voltage and output voltage. So we need to use the fact that the net change in inductor current is 0. This is the assumption 1, that the circuit works in steady state. In steady state means that the increase plus the decrease here equals 0. So I give you 30 seconds to write down the equation and simplify the equation to obtain the relationship between Vs and Vo. Okay, let's take a look. So use the fact that delta IL closed plus delta IL open equals 0. We plug in their expressions and simplify the equation. We can obtain the relationship between the input voltage and output voltage. So here the 1 minus D is a value between 0 to 1. So the output voltage VO is greater than Vs. Or if the source voltage is a fixed value, we can adjust D, the duty ratio, in order to adjust the output voltage. In converter design problems, sometimes the input voltage is given, and also they have a requirement on the output voltage. So you need to calculate the duty ratio. Next, we need to derive the average current of the inductor and the maximum and minimum inductor current, and what is the requirement for continuous inductor current. So here we already know delta IL, right? So if we obtain the average value by plus or minus half of delta IL, we can obtain the Imax and I minimum. So how to calculate the average value? Give you 1 minute to think about it. So I give you a hint, that is, use the power balance equation, that is the input power equals output power, to obtain the average value of the inductor current. So give you 1 minute to think about it. Okay, let's take a look at this problem together. So the input power is represented by PS, and the output power is represented by PO. So PS equals VS times IL, and PO equals VO squared over R. So we also know the relationship between VO and VS. So by simplifying this equation, we can obtain the expression for IL. This is the expression for IL. Once we obtain the expression for average inductor current, we can calculate the maximum inductor current by plus half of delta IL. And the minimum inductor current can be obtained by minus half of the inductor current. So here we obtained the expression for the minimum current, that is the current here. In order to guarantee that the circuit works in continuous current mode, we need to make sure that the I minimum is greater or equal to 0, because all our analysis were based on the fact that the circuit works in continuous current mode. If it works in discontinuous current mode, we will discuss this in future lectures. So we have obtained the minimum current, and in order to guarantee continuous current operation, the inductor current must be positive. So by setting the minimum value to 0, we can obtain the minimum value for the inductor inductance. So this means that if we want the circuit work in continuous current mode, we need to select the inductance of the inductor to be greater or equal to the L minimum. Next, let's discuss the voltage ripple, the output voltage ripple. The previous analysis were developed based on the assumption that the output voltage was a constant, which means that the capacitance is infinite large. But in practice, a finite capacitance will result in some fluctuations in the output voltage, and this is called voltage ripple, because we charge and discharge the capacitor, so there will be ripples on the capacitor voltage. So now let's take a look on how to calculate the voltage ripple. So that is question 14. Derive the relationship between voltage ripple and the capacitance of the capacitor. So this figure shows the current of the capacitor. When the switch is closed, the current is negative VO over R. So we can calculate delta Q using the current times the dt. So we can obtain delta Q. And we also know delta Q equals the capacitance times the delta VO, that is the voltage ripple. So we can easily obtain the equation for delta VO. From this equation, we know that if the C, that is the capacitance, is infinite large, delta VO is close to 0. But in fact, the C cannot be infinite large. So by given the value of C, we can calculate delta VO. But in order to make the voltage ripple small, we want a large capacitance. So that's all for today's lecture, and let's have a brief review. So today we discussed the basic principle of DC-DC converter and introduced the method to analyze DC-DC converter. That is to discuss two scenarios when the switch is open and when the switch is closed, and plot the equivalent circuit and plot the waveform, the current and voltage waveform on each component, and using the fact that the circuit is operating in steady state, so that the current change in inductor in one period, the net change of inductor current in one period equals 0, we can derive the relationship of input and output voltage. That's how we analyze boost converter. So in our homework, you will be asked to analyze the input and output relationship of buck converter, which is another DC-DC converter, and its output voltage is lower than the input voltage, but the method is the same. So this is the first homework. Next, you will be asked to carry out PSpice simulation on boost converter and finish problems on the homework. And also the discussions and questions, you can post your questions on Piazza and have the discussion on Piazza. And the course video and the solution to the previous assignment will be uploaded on YouTube or Youku, the Chinese counterpart of YouTube. Now let's come back to the learning objective and check whether you meet the learning objective. So the first is comprehend the working principle of boost converter. So if you had no problem answering the questions on my lecture note, you comprehended the working principle of the boost converter. The next is that you will be able to carry out analysis on other DC-DC converter. So this will be based on the feedback of your homework. If you had no problem doing your homework, you meet the second learning objective. That's all for today's lecture, and questions and welcomed. Do you have any questions?